6 topics under the unit 1. Right, 6 topics under the unit 1. Those are the we have already done up to now 4 topics. Right. Okay, now we have to consider fifth topic is the ionization energy. That's very important topic. Therefore, we have to consider this ionization energy. Okay. Write the topic as ionization energy. Right. Okay, under that, write the topic as first ionization energy. First ionization energy. That write the topic as first ionization energy. Okay. As you can see here, when we consider the definition of the first ionization energy, this is the definition of the first ionization energy. This is not the first time that you are hear about this first ionization energy. You have already heard about this in grade 10, and grade 11, right? The O-level period also you have already discussed about the ionization energy. Okay, when we consider the ionization energy, assume the atom called A. Assume the atom called A, right? It should be in the gaseous state, right? Every time it should be in the gaseous state, but it cannot be existed in the liquid state or aqueous state, right? It should be in the gaseous state, right? When we consider the minimum energy required to remove the most loosely bounded electron from a neutral gaseous atom, this is the neutral gaseous atom, right? Neutral gaseous atom, right? This is the electron removed from the loosely bounded electron from the neutral gases, right? Neutral gaseous atom to form a gaseous unipositive cation. This is the gaseous unipositive. After releasing electrons to the media, right, it can be produced the gaseous state unipositive ion. The energy that we want to release like that electron, it is the energy that we want to give this atom, it is known as the first ionization energy, right? When we consider several examples for this, when we substitutes for the A, sodium and magnesium, we substitute atoms for the A, sodium and magnesium, we are able to write down here, right? As you can see, there is a sodium, the gaseous state. After releasing one electron, it can be produced the gaseous state sodium ion. This is the common equation. This is the general equation for the first ionization energy. If it is first ionization energy, we are going to indicate it using the IE1, first ionization energy, right? Okay. This is the common mistake alert. What are the common mistakes, students, Adam, when we are doing the when we are referring this first ionization energy? Always include the state symbol. Look at this. Always include the state symbol. It shouldn't be liquid or aqueous medium. Every time it should be the gases. It should be the gases, right? In your exam answers, removing an electron from a solid or liquid requires different energy. It means sublimation or vaporization. We will discuss those things, right? In the future. The gaseous state is mandatory for the mark, right? You have to mark you must mark the gaseous state, otherwise it will be wrong, right? Okay. Now you know these things you have already discussed in grade 10 also, right? Do you remember first definition of the first ionization energy? That is I have included here, right? The minimum energy required, again, let's describe about that. The minimum energy required to remove the most loosely bounded electron from a neutral gaseous atom, right? I have highlighted that. Neutral gaseous atom to form gaseous unipositive cation, right? It can be produced the gaseous unipositive cation, right? Okay. Now let's move to the another point. The another point is the four controllers of ionization energy. Okay, what are the factors affect to this ionization energy? Right? There are mainly two factors affect to the ionization energy. Right? Mainly it has included two factors. As you can see, okay, this ionization energy is not random. It's governed by a delicate balance of four atomic forces. What are the factors? I have already mentioned here. The factors affect to the ionization energy. Mainly it has included two factors. The first one is atomic radius. The atomic radius is mainly affected to the ionization energy. Another one is electron configuration. Right? Another one is electron configuration. Now I have told you there are mainly four factors affect to the ionization energy. What are those? First one is, remember this, atomic radius. Atomic radius. Another one is, tell me, electron configuration. Right? Then, do you remember the two factors can be affected to the atomic radius? Those are the effective nuclear charge. We have already mentioned that is it effective, right? Do you remember the is it effective? We have already discussed. The first one is effective nuclear charge. Another one is first that is the yes screening effect. There is another name for that. Shielding effect. Screening effect or shielding effect. These are the main two factors affected to the ionization energy. These two factors are affected to the atomic radius. Due to that reason, atomic radius can be affected to the directly ionization energy. It means these both factors can be affected to the indirectly ionization energy. Right? Okay. Now let's consider how to affect this atomic radius to the ionization energy and electron configuration, how to affect the ionization energy. Okay. Okay. Let's write down note. Let's write down note. Up to now we have discussed these. Let's write down these things. Okay. Now first of all, let's write down definition of the ionization energy. Okay. Write down here. When we consider the definition of the ionization energy, we are able to write down here. We do write the first ionization energy. Within the brackets, write down. We are able to indicate this first ionization energy. First, IE, ionization energy. Otherwise, we are able to tell IE1, I1 also. Right? Okay. Now let's write down definition of the first ionization energy. The minimum energy required to, that's the definition. The minimum energy required to remove the most loosely bound. The minimum energy required to remove the most loosely bound. The minimum energy required to remove the most loosely bound electron from a neutral gaseous atom to form a gaseous unipositive. Unipositive means univalent, no? Univalent, right? Otherwise, we are going to tell the monovalent, otherwise monopositive, right? Unipositive. Cation is the first ionization energy. Unipositive. Cation is the first ionization energy. Simply we are going to tell IE1, right? IE1. Simply we are going to tell IE1. Okay. Within the brackets, write down IE1. Okay, let's write down common formula for the first ionization energy. If it is first ionization energy, the reactant side there should be a neutral state atom. After releasing one electron, it can be produced the gaseous state unipositive or univalent cation. Right? Okay, write down this. This is the common formula, and also we have to write down examples for this formula. When we substitute sodium and magnesium atoms for the A gas, right? This common formula, we are going to obtain the first ionization energy of sodium and first ionization energy of magnesium, right? This is a common mistake alert. I have already told this. Always include the state symbols. It means gas in your exam answers. Without that, it will be wrong. Right. Write the examples also. Right? Okay. Now let's go to the, I have already discussed now. There are mainly 4 factors affect to the first ionization energy. It has included mainly 2 factors. Both factors can be affected to the ionization energy directly. But both factors, it means effective nuclear charge and the screening effect, both factors can be affected to the atomic radius directly. This atomic radius can be affected to the ionization energy directly. Then it means both factors can be affected to the ionization energy indirectly. Indirectly, right? Means there are mainly 2 factors, and in addition to there are another 2 factors affected to the ionization energy. Right? Okay, let's write down these things one by one. Write down here. Ionization energy is, as a point, write down. Ionization energy is mainly influenced. Ionization energy is mainly influenced by 2 factors. Mainly influenced by 2 factors. Right? Okay, write down first one. We know main factors are, the first one is atomic radius. The atomic radius. The second one should be electronic configuration. Electronic configuration. Right. Next point. Write down as a point. Write down here. Additionally, I have told you, in additionally there are another 2 factors. Right. Additionally, it is influenced by the nuclear charge. Additionally, it is influenced by the nuclear charge. Right? The nuclear charge should be effective nuclear charge. Within the brackets, write down is the defective. In here we are going to consider the not nuclear charge, it should be effective nuclear charge. The effective nuclear charge and the screening effect are the 2 factors affected to the atomic radius. No? Okay. Then influenced by the nuclear charge and the screening effect, along a period. And the spreading effect, okay? Check here as a full stop. Next point. Okay, then tell me what will happen when we go through left to right each of every period. We know second and third period elements, the hydrogen and helium elements are in the first period now. Is the very short period, right? But when we consider the second and third period, it has included 8 number of elements. Right, second period it has included 8 number of elements, and third period also it has included 8 number of elements. Right? Okay. Now, most probably we are going to discuss the second and third period. Right, friends? You do remember the trends of the atomic periodic table? We have discussed, no? Electron affinity, electron gain energy, oxidizing ability, and the ability to produce the cation and anion, right? Electronegativity, electropositivity, right? Melting point, boiling point, those are the things that we have already discussed. Trend of the periodic table. Same as in ionization energy also. When we discuss the ionization energy, what will happen when we go through left to right each of every period? It will describe using the atomic radius, right? Do you remember the atomic radius? These two factors are affected to the atomic radius. You know, when we go through left to right each of every period, the radius, atomic radius can be decreased. You remember? The reason is the effective nuclear charge can be increased. If the effective nuclear charge can be increased, is directly proportional to the directly or inversely proportional. If the effective nuclear charge can be increased, the atomic radius should be decreased. Those are the inversely proportional two factors, right? Then as radius decreases, ionization energy increases. What's the reason for that? If the atomic radius increases, what's the reason for increasing the ionization energy? You know, we have already defined the ionization energy now, right? It has included the minimum energy required to remove the most loosely bound electron from the neutral gaseous element. Where's the location of the most loosely bounded electrons in the atom? The location of the most loosely bound electrons in the valence shell, right? Valence shell, no? Right? To release the electrons from the valence shell, when the distance between nucleus and the valence shell decreases, when the distance between nucleus and the valence shell decreases, then is it difficult or is it easy to remove the electrons from the valence shell? It's difficult. It's difficult to remove the electrons. The reason is attraction forces between nucleus and the valence shell electrons are increased. That's the reason. That's the reason I have mentioned here. Yes, across a period. Look at this. The navigating the periodic laws, when we consider the across a period, left to right, the ionization energy increases. The main reason is why? The atomic number increases, electrons add to the same shell. It means effective nuclear charge increase, right? Effective nuclear charge increases. The shrink in the radius and pulling electrons, right? It's difficult to release electrons from the valence shell, right? You remember? Then the opposite process can be happen when we go through top to bottom each of every group. The reason is top to bottom, the atomic radius increases. If the atomic radius increases, then it means if the atomic radius increases, the attraction forces between nucleus and the valence shell electrons decreases. The reason is the distance will be can be obtained the higher value when we go through top to bottom, right? Then descend in each of every group, then what will happen? If the atomic radius increases, it's easy to remove the electron from the valence shell. It's easy to remove the electron from the valence, right? Okay, when we consider about the top to bottom down group, the ionization energy decreases. Remember about this? Okay, look at this. What is the reason for that? The main reason is electrons are added to new further energy levels. You know, the first period it has included valence shell in the first energy level. Second period, if the element is in the second period, the valence shell should be the second energy level. If the elements are in the third period, valence shell in the third energy level, it means the distance between nucleus and the valence shell increases, right? Okay, further energy levels, the atomic radius grows and the screening effect increased. What's the reason for increasing the screening effect? When we go through top to bottom each of every group, the reason is I have already mentioned about that previously. What's the reason? The reason is, what's the reason for increasing the screening effect or shielding effect? The number of inner energy levels can be increased. The number of inner energy levels can be increased if it is happening like that, then screening effect also increases, right? The repulsion forces between electrons and electrons can be increases, no? That's the main reason. Okay. Then overpowering the nuclear charge, right? These are the main points that you have to remember. Okay, there is this exam tip here. Under the D block metals, D block metals are known as, I have already told about this when we are discussing the periodic table. Then transition metals do not show a regular increase. The elements which are included in the D blocks, those are known as most of the elements can be existed as the transition metals. Transition metals, right? These transition metals do not show a regular increase of the atomic radius, right? But rather a gradual increase across the period, right? It can be obtained the gradual increase across the period, right? Okay. Let's write down these things, left to right and the top to bottom of every page. And also we are going to draw the how about the shape, left to right each of every period. It cannot be increase the ionization energy gradually when we go through left to right each of every period. There are several deviations. There are several deviations when we go through. Most probably we are telling the ionization energy can be increased. The reason is the atomic radius and the atomic radius. When I have told you there are mainly two factors affect to the ionization energy. Only we are consider the atomic radius. According to that factor, the ionization energy increases left to right. But when we consider the another factor, stable electron configuration, right? Using this stable electron configuration, it will deviate. It will deviate, right? Okay, let's write down these things. Write down here. Next point. Along a period from left to right. Along a period from left to right. Along a period from left to right. Along a period from left to right, along a period from left to right, as the radius decreases, as the radius decreases, comma, the ionization energy increases. The ionization energy increases. The ionization energy increases, right? These are the points that you have to remember, right? As I mentioned previously. Okay, next point, write down next point. Write down these things one by one, point by point. Okay, the next point. The primary reason is, right? The primary reason is that along a period. The primary reason is that along a period, the atomic number increases, comma, and electrons are added to, the same energy level. I have already mentioned about that, right? Previously, I have told you this is the main reason, right? To increase the ionization energy when we go through left to right each of every period, right? Especially second and third period, right? Okay. And electrons are added to the same energy level, right? Full stop. Then write down that point. This increases the effective nuclear charge. This increases the effective nuclear charge, comma, pulling electrons, right? Pulling electrons more strongly, pulling electrons more strongly. More strong. Right. Next point. Write down next point. Therefore, more energy must be supplied. Therefore, more energy must be supplied. Therefore, more energy must be supplied. More energy must be supplied to remove an electron. To remove an electron. Therefore, more energy must be supplied to remove an electron. To remove an electron from a smaller atom. To remove an electron from a smaller atom. To remove an electron from a smaller atom. Thus, write down that point. Thus, the first ionization energy increases. Thus, the first ionization energy increases. The first ionization energy increases. Okay, I have already discussed what will happen when we go through top to bottom each of every group. Okay. Down a group, what will happen? Let's remember again. Electrons are added to new further energy levels. The atomic radius grows and the strain effect increases, overpowering the nuclear charge. It means if the nuclear charge is overpowering, is it difficult to, is it easy to release the electrons from the valence shell? It's easy to release the electrons from the valence, right? Okay, then write down a group from top to bottom. 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 The first ionization energy. The first ionization energy. Down a group from top to bottom. The first ionization energy decreases. The first ionization energy decreases. The main reason is the increase. The main reason is the increase in atomic radius, right? After increasing the after increasing the screening effect, after increasing the screening effect or shielding effect, you know that factor is directly proportional to the atomic radius. When the screening effect or shielding effect can be increased, then atomic radius also increased. That's the main point, right? The reason is increase in atomic radius, right? Okay. Now let's move to another point. As you go down a group, write down next point. As you go down a group, electrons are added to new energy levels. 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 Further from the nucleus. Right? I have already mentioned those things in this point. As you go down a group, electrons are added to new energy levels further from the nucleus. Next point. Consequently, the screening effect increases. Consequently, the screening effect increases. The screening effect increases. The screening effect increases, and the attraction of the nucleus. And the attraction of the nucleus. And the attraction of the nucleus on the outermost electron decreases. And the attraction of the nucleus. And the attraction of the nucleus on the outermost electron. On the outermost electron decreases. on the outermost electron decreases. On the outermost electrons decreases. Full stop. Therefore, the first ionization energy decreases. Therefore, the first ionization energy decreases. Therefore, the first ionization energy decreases. Okay. Now we are going to draw the first ionization energy. And here we are going to consider, I am going to obtain the factor for the y-axis. Look at this. Okay. Then y-axis first ionization energy, x-axis, I have obtained the atomic number. Right? In here also, we are not going to consider d block elements. Right? I have told you what's the reason for that. This is the reason transition metals do not show a regular increase. When we consider the representative elements, what's from these representative elements? I have already told you S block and P block elements. Right? When we obtain together S block and P block elements, those are known as representative elements. And what's another name? Main group elements. No? Main group elements. Except these S and P block elements, all of the D block elements, right? We are able to tell that there are no any regular increases of the atomic radius. Due to that reason, there are no any gradual increase across a period under the ionization energy. Right? Here we are discussing the first ionization energy up to now. This is the graph of the first ionization energy. Right? Now we are going to draw the graph of the first ionization energy. Before that, I am going to draw the the atomic number. First of all, let's consider only one period. I am not going to consider these are the periods. No, hydrogen and helium is in the first period. This is another period from lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. This is the second period. Then sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, argon. This is the third period. Potassium, calcium, fourth period. Right? Among 20 elements, we are able to include this 20 elements to the 4 periods. 4 periods. You know about that, right? Okay. Now I will consider. Look at this. I will consider only one period. I am not going to consider all of the 4 periods. In this situation, I am going to consider only one period. Look at this. Now I am going to draw the same as in this graph. I will write the group. The factor I am going to obtain the x-axis as the group, right? Group number. Right? We know the first and second group are included in the S block. Then group 13 to group 18 groups are included for the P block. Right? These are the blocks that we are going to consider here. This is the first ionization energy. In here we are going to write the kilojoule per mole. Right? Okay, look at this. When we are drawing the graph of the first ionization energy, I have told you there are two factors affected to the ionization energy. No, there are 2 factors. What are those? Mainly 2 factors, but it has included 4 factors with the screening effect and effective nuclear charge. Except these additional factors, there are mainly 2 factors affected to the ionization energy. Both are the atomic radius and the stable electron configuration. Right? This is the first group. And the second group, I am going to assign the groups here. Right? Then group 13, 14, 15, 16, 17 and 18. These are the groups. Right? Okay. Now look at this. I will draw like this. Listen to me carefully. Okay. Now I am going to draw. How about the how to increase? I have already mentioned when we go through left to right each of every period, the ionization energy increases. The reason is atomic radius decreases. No, if the atomic radius decreases, the ionization energy increases. Okay. Now I am going to consider only that factor, right? According to that factor, when we go through left to right, the ionization energy increases. No? Then this is the first group ionization energy. The energy of the second group elements, the ionization energy of the second group elements are greater than the ionization energy of the first group elements. What's the reason for that? The ionization energy of the second group elements are greater than the ionization energy of the first group elements. What's the main reason? The reason is atomic radius of the second group elements are lower than the atomic radius of the first group elements. I have told you atomic radius, if the atomic radius decreases, the ionization energy increases. According to that, we know left to right when we go through every period, then the ionization energy of group 13 elements should be greater than the ionization energy of first and second group elements. Like that, we are going to write down here, no? For likewise, I will do. It can be increased gradually. But the problem is, in here I have drawn the ionization energy graph according to atomic radius. In here I have only considered the only one factor, atomic radius, but I haven't considered here what's another factor? Stable electron configuration, right? When we consider about that factor also, previously I have mentioned 4 factors affect to the ionization energy. Among these 4 factors, the electron configuration is another main factor, right? Another main factor is electron configuration. Okay. Then, when we consider the electron configuration, right? Look at this. Stability. The stable electron configuration. Tell me, is it easy to remove the electrons from the stable electron configuration or not? If the energy level is already existed as the stable electron configuration, is it difficult or is it easy to remove the electrons from that energy level? It's difficult. Eh? The reason is after releasing electrons, it may be unstable. After releasing electrons, if it is obtained the unstable electron configuration, it's difficult to release the electrons from that energy level. That's the main reason, right? Look at this. Stable, fully filled or half-filled configurations require significantly more energy to break, right? Require significantly more energy to break. Okay. According to that factor, I'm going to draw this. Energy graph. Look at this. We know. Then tell me how to write look at this. How to write the valential electron configuration of the group 1 elements. Then tell me how many valential electrons in the group 1 elements. If it is group 1, there is only 1 electrons in the valence shell. If the elements are in the group 2, there are 2 electrons in the valence shell. If the elements are in the group 13, there are 3 electrons in the valence shell. If the elements are in the group 14, there are 4 valence shell electrons. If the elements are in the group 15, there are 5 electrons in the valence shell. Likewise, if the electrons are in the group 16, there should be 6 electrons in the valence shell. If the electrons are, if the elements are in the group 17, 18, there should be 7 and 8 valence shell. Okay, according to that, group 1 and 2 are included for the S block. No, due to that reason, I am able to write down there should be only 1 electrons in the S orbital. The valence shell should be, the valence shell is, if it is group 1, then I am able to write down S1. This is the valence shell electron configuration, right? Then if it is, if the elements are in the second, look at this, second period, second group, how many valence shell electrons it has included? There should be 2 valence shell electrons. Both first and second group are included for the S block now. Due to that reason, I am writing here S1, S2. Likewise. But when we consider group 13 to group 18, those are included in the P block. Then how to write the, then tell me, how to write the valence shell electron configuration of the group 13 elements? If it is, if the elements are in the group 13, I have already mentioned how many valence shell electrons? It has included 3 valence shell electrons now. It has included 3 valence shell electrons. Then how can we fill 3 valence shell electrons? S and P orbitals. First of all, it should be completed 2 electrons for the S and another remaining electrons can be obtained P. Now it's already completed S2P. Okay, this is the deviation point. And tell me, this is the deviation point. Look at this. Okay, as you can see here, look at this. Beryllium, I will describe here. The beryllium, when we consider beryllium is in the second period element, second group element, right? Beryllium is the second group S block element. Beryllium, magnesium, calcium, strontium, barium, those are the second group elements. When we consider second period, second group elements, it should be beryllium. Okay, the electron configuration is S2. Then tell me, is it stable or unstable electron configuration? Previously, I have mentioned you, if the subshell, right? If the subshell can be obtained maximum number of electrons, it should be the stable electron configuration, right? Then S2 is the stable electron configuration. Then valence is S2. But when we consider the boron, what is the adjacent elements to the beryllium? What is the another adjacent elements to the beryllium? Boron, no? Boron. The adjacent element is boron. And when we consider the electron configuration, valence shell electron configuration of boron, it should be S2, S2P1. But it is stable or unstable? Unstable. Then I have already mentioned you. Look at this. The fully filled S2 configuration is more stable than S2P1. This is the unstable electron configuration. S2P1. The removing the single stable fully filled S2 configuration, P1 electron is easier, right? It is easy to remove the electrons from the boron. It's difficult to remove the electrons from the beryllium. That's the reason for deviation. That's the reason for showing the deviation in this form, right? Okay, look at this. Then when we consider the first ionization energy of the group 13 elements are lower than the first ionization energy of the group 2 elements, right? Can you understand about that? Right? Then this should be S2, S2P1. The next one, what will happen next one? Then we know group 14, how many valence shell electrons? Group 14, 4 valence shell electrons. When we go through group 13 to group 14, the atomic radius decreases, then it means ionization energy increases. We consider the another factor is electron configuration. If there are 4 electrons, how to write that? S2P2, S2P2, like Both are stable or unstable? Both are unstable. Then which factor we are going to obtain the ionization energy? Which factor we are going to describe the ionization energy? Both are equal. Equal means unstable. Then atomic radius factor we have to obtain to describe this. Then we know the atomic radius of group 14 is lower than the atomic radius of group 13. Due to that reason, the first ionization energy of the group 13 elements are lower than the first ionization energy of the group 14 elements. Right? Okay. Group 15. Look at this. It's very important. When we consider the group 15 elements, how many valence shell electrons that can be included? Group 15? 5. How can we fill 5? S2P 3. Then tell me, is it stable electron configuration or unstable? Is the halfly filled? No, halfly filled. Then, if it is S2P3, the P subshell is already halfly filled. Due to that reason, it is stable electron configuration. Halfly filled? No, halfly stable. Then, when we compare these two electron configurations, the electron configuration of the group 15 elements are greater than the stability of the electron configuration. The stability of the electron configuration of the group 15 elements are greater than the stability of the group 14 elements. Then the ionization energy should be increased or decreased. Yes, this should be increased. Right? We are going to write down here. Right? Okay, when we consider the group 16 elements, how many valence shell electrons are existed? Group 16 elements? 6. How can be filled? S2, P4, then 4 plus 2 is 6. Right? Okay. When we consider in this situation, these adjacent groups, look at this, when we go through left to right, the atomic radius increases. Due to that reason, previously, it has already increased ionization energy when we consider these 15 and 16 groups. But in here, electron configuration, the stability of the electron configuration of the group 15 are greater than the stability of the group 16 elements. Right? Can you understand? Due to that reason, in this situation also, it's difficult to remove the electrons from the valence shell of the group 15 elements. Right? It's easy to, when we compare these two adjacent groups, it's easy to release the electrons from the group 16. Due to that reason, right, look at this, the ionization energy, first ionization energy is lower than the first ionization energy of the group 15 elements, right? Like this here. Okay, next one, when we consider another, these two adjacent groups, the atomic radius also, I will write this here, S2P4. Okay. When we go through group 16 to group 17, atomic radius decreases, it means ionization energy increases. Then the electron configuration of the group 17 is stable or unstable. How can we fill electrons of the group 17 valence shell? S2, tell me, S2P5, no? 5 plus 2, 7. Both are unstable. No? Then which factor we are going to describe the ionization energy? Atomic radius. According to that factor, then if the atomic radius is decreased, the ionization energy can be increased. Like this. Right? Okay. The next one, same as previous one. When we consider overall period from first group to 18th group, which group can be obtained the, right? Which group can be obtained the most stable electron configuration? Group 80. Most stable electron configuration. The reason is all of the energy, sub-energy levels, it means S2P 6. Right? If the elements are in the group 18, tell me how many valence shell electrons that can be included? 8. Then how can we fill it? S2P 6. S2P 6. Like this. Okay. Okay. There is a name for this shape. What's the name for this shape? Zigzag. Zigzag. Zig. This is the name for this shape. Right? It cannot be increase the ionization energy gradually. When we go through left to right each of every field, there are several deviations here. Where are the locations of the deviation? When we go through from second group to 13th group and the 15th group to 16. Right? Can you understand? Here also I have already described. This is also the anomaly, right? Then as I shown you, right? This is the deviation point, group 50, when we go through group 15 to group 16, right? Let's write down these things one by one. Okay, write down here. Right. Okay, first of all, draw this graph. Try to draw this graph. Then we will describe what will happen here. Okay, let's write down the note. Write down here. The deviation seen between this deviations seen between the deviations seen between group 2 to 13. The deviations seen between group 2 to 13 and group 15 to 16. As you can see, both graphs are identical, okay? It has included 4 periods. I have already drawn the 1 period. It may be second or third period. Right? Okay, let's write down. Groups 15 to 16 are due to the stability of 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 half filled half filled and fully filled and fully filled and fully filled electronic configurations electronic configurations electronic configurations electronic configurations in the outermost shells in the outermost shells in the outermost shells of those elements the outermost shells of those elements okay, write down next point. The reason for now we are going to write down the reason for what's the deviation, what's the reason for deviation these groups when we are go through from second group to group 30, right? I have already mentioned about that. Now let's write down the reason for IE1 means first ionization energy IE1 of group 13 the reason for IE1 of group 13 being lower than group 2 being lower than group 2 right? As you can see here also I have already mentioned. Okay, let's write down these things. These are the main factors Main reasons. Okay, let's write down. I'm going to describe this using 4 points. Try to remember these 4 points. Right? Okay. Now I am going to tell the reasons for first ionization energy of group 13 being lower than group 2. I'm going to describe this using 4 points. Try to remember these 4 points using the stable electrode configuration. Right? Okay. Write down first point. The valence configuration of beryllium. The valence configuration of beryllium is in the group 2. Okay. The valence configuration of beryllium. The valence configuration of beryllium within the brackets write down group 2 is S2 is S2, right? If it is magnesium it may be 3S2. If it is beryllium it should be 2S2. Likewise all of the elements that are included in the group 2 elements, right? The valence configuration of beryllium is S2, comma, while boron within the brackets write down group 30. While boron within the brackets write down group 30, close the bracket and is S2P1, while boron is S2P1. S2P1. Next point. The S2 configuration is more stable. The S2 configuration is more stable. The S2 configuration is more stable. The S2 configuration is more stable than S2P1. Then S2P1. Then S2P1. Next point. Therefore, more energy is required to remove. Therefore, more energy is required to remove. More energy is required to remove. Therefore, more energy is required to remove an electron from more energy is required to remove an electron from the stable S2 configuration. The stable S2 configuration. The stable S2 configuration of beryllium. Next point. Thus IE1 means first ionization energy. Thus IE1 of boron is lower than that of beryllium. Lower than that of beryllium. Right. That is how to describe this anomaly. Right. When we go through left to right, each of every period, you know, the first ionization energy is group 2 is greater than the first ionization energy of the group 30. Right. That's the anomaly. Can be shown the anomaly here. Right. These are the 4 factors, right, described in this. What's the reason for anomaly? Okay. Same as there's another one you are able to see like that anomaly. It can be happen when we go through group 15 to group 16. It also we are going to write down. Let's write down here. The reason for IE1 of the reason for IE1, it means first ionization energy. IE1 of group 16 being lower than group 16 being lower than group 15 for nitrogen and oxygen. The reason for IE1 of group 16 being lower than group 15 for nitrogen and oxygen. Right? Okay. Then write down here. In here also I am going to describe this using 4 factors, 4 points. Write down this. First point, the valence configuration of now you are able to write down, right? It is same as previous exam. The valence configuration of nitrogen is the valence configuration of nitrogen is S2P3. S2P3. The valence configuration of nitrogen is S2P3, while oxygen is S2P4. While oxygen is S2P4. While oxygen is S2P4. Right? Okay, write the next point. Next point. The S2P3 configuration is the S2P3 configuration is more stable than the S2P3 configuration is more stable than S2P4. The S2P3 configuration is more stable than S2P4. We know the electron configuration of nitrogen is valential electron configuration is of nitrogen is S2P3. Then what will be the valential electron configuration of the oxygen? It should be S2P4. Now you know it has already halfly filled electron configuration of nitrogen S2P3, but it can be obtained the unstable electron configuration for the oxygen. That's the main reason to show the anomaly process here, right? Okay, then write down. The S2P3 configuration is more stable than S2P4 because it is half filled. Because it is half filled, right? Because it is half filled. Because it is half filled. Next point. Therefore, more energy is required to remove. Therefore, more energy is required to remove. Therefore, more energy is required to remove an electron from Therefore, more energy is required to remove an electron from the stable half-filled configuration of nitrogen. The stable half-filled configuration of nitrogen. The stable half-filled configuration of nitrogen. Next point. Thus IE1 of oxygen is IE1 means first ionization energy. IE1 of oxygen is lower than that of nitrogen. IE1 of oxygen is lower than that of nitrogen. Right? Okay. Now we are going to know this. These are the main factors. How to describe the anomaly process when we go through between group 2 and group 13 and also group 15 and group 16. Right? And when we consider another point, second and third ionization energy, before move to the second and third ionization energy, we are going to describe we are going to draw the 20 elements. You know the from hydrogen to calcium has 20 elements. There are 20 elements. It has included 20 elements between hydrogen and calcium. We are going to draw the first ionization graph. Right? After including these 20 elements, all of the 20 elements are included this one graph. Right? It is the first ionization graph. Okay, now I am going to draw it. Before that, let's write down it. Write down here. The first ionization energy graph for elements with the first ionization energy graph for elements with atomic numbers, elements with atomic numbers 1 to 20, 1 to 20, 1 to 20 in the periodic table is shown below. In the periodic table is shown below. In the periodic table is shown below. Okay. Now let's draw the ionization energy graph. Right? I'm going to obtain the first ionization energy for the y-axis, same as previous one. Then elements are in the 20 elements are in the x-axis. Right? The same as previous. This is the first ionization energy graph. I'm going to draw this. Right? Okay. Then look at this. How to draw this graph? You should have the ability to draw this graph immediately. When you are writing the Excel, if they have given the questions from this ionization energy, to prepare the elements ascending or descending order first ionization energy. In that situation, you should have the ability to draw this graph immediately. Right? After drawing this graph, you are able to prepare the ascending or descending order of the elements of the first ionization energy. Right? Can you understand? Okay, look at this. Now I am going to draw there is a method to draw this first ionization energy graph. There is a method for it. Look at this. This is the method. Try to practice this method. Right? This is the first ionization energy IE1. It should be kilojoule per mole. This is the unit for the first ionization energy. You have already discussed this in grade 10 also. Right? Then I am going to put the factor as the x-axis elements. There should be 20 elements. Right? Look at this. Now, yes, this is how to draw the ionization energy graph. First of all, you have to start from the middle state. Right? Look at this. First of all, you have to start from the second period. Now I am going to draw the first ionization energy graph for the fourth periods. From first to fourth period. Look at this. Now I am going to start the middle period. It means second period like this. This is the shape now. I have already told you the shape. What is known this shape? Zigzag shape. Right? Okay. There is a element here below this line. That's element here below this line. And also there is an element here over this line. Over this. Right? Okay. The next one. Look at this. Now I am going to repeat this shape below as the third period, and also I am going to stop that line from this end of the line. Right? Now I am going to complete here, and also I am going to attach these two lines, and also I am going to attach these two lines. That's how to draw the first ionization energy graph. Right? That's how to draw the first ionization energy graph. The shape of the first, second, third ionization energy graphs are identical. There are no any changes. The shapes of the first, second, third ionization energy graphs. Right? But the element that we are going to start, it can be changed. The element that we are going to start here, if it is first ionization energy, we are going to start from the first element. You know the first element is the hydrogen. If it is second ionization energy, if they have asked from us the second ionization energy, try to prepare the ascending or descending order of the second ionization energy. We are going to start the second element. What's the second element? Helium. If they have asked from us the third ionization energy, you are going to start from the third elements called the lithium. The shape of the first and second and third ionization energy graphs are the identical. They cannot be changed. Right? The same way you are able to draw this. Right? Okay. If this is first ionization energy, I am going to start from the hydrogen. Then this should be hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, argon, potassium, calcium. You should have the ability to draw this immediately in the A-level Excel. Right? I will do the past paper questions at the end of this lesson also. I will show you how to do the questions. Right? That they have given for us. Okay. Now, as you can see here, the peak points. When we consider the peak points, these are the peak points now. Helium, neon, argon. Which type of elements can we obtain the peak points? Helium, neon, argon, krypton, xenon, radon. Those are the group 18 elements. Normal gases. What's the reason for obtaining the highest first ionization energy values for these noble gas elements? Otherwise, rare gas elements, those are known as. What's the reason? Yes, due to the stable electron configuration, right? As you can see here, helium, neon, argon, they have included the stable valence shell electron configuration. After releasing electron, it cannot be obtained the stable electron configuration. It will be unstable. Due to that reason, it's difficult to release the electrons from the valence shell, right? Okay. Noble gases sit at the absolute peaks because they have very stable, fully filled outermost shells in their natural state, right? They are neutral state. Neutral state means ground state, right? Otherwise they cannot be created the anion or cation. The reason also they have the stable electron configuration in the ground state. Okay, when we consider the elements are in the ground state, troughs. Elements are in the troughs. These are the peak points, these are the troughs. Then tell me which type of groups elements are in the trough points. Lithium, sodium, potassium, those are the first group elements. What's the reason for obtaining the low first ionization energy values for the first group elements? We know the all of the periodic table. Among all of the periodic table, which group has the highest atomic radius? First group elements has the highest atomic radius. Atomic radius, no. Then, if they have obtained the highest atomic radius, the distance between nucleus and the valence shell increases, no? Then attraction forces between nucleus and the valence shell electrons are the decreases, no? Then it's easy to remove the electrons from the valence shell and it can be created unipositive gaseous state ion. It's easy to do that. That's the main reason for obtaining the lowest first ionization energy from the group 1 elements. Alkali metals, I have already told you, group 1 elements can be known as the, there is a name for it. They are known as the alkali metals. Group 2 elements, alkali earth metals, right? When alkali metals sit at the absolute trough, because they have the largest atomic radius in their period and the lowest effective nuclear charge. Then we consider the effective nuclear charge also. Group 1 elements have the lowest effective nuclear charge. Right? Can you understand? Okay. Let's write down these things. And also exam tip. Memorize the shape of this curve. Exam questions often show a nameless snippets of this graph and ask you to identify the elements. We will do several past paper questions that they have given for us previously. I will do these things with you. Okay. Can you understand these things? Okay. Now let's write down these things. Hurry up. Okay. First of all, let's draw the this graph. No need to draw this graph. Try to draw this graph. First ionization energy graph. Okay, then let's write down these things. According to this first ionization graph, you are able to see the peak values can be obtained the noble gases, group 18 elements, and the trough points can be obtained the group 1 elements. It means alkali metals, right? Then the highest first ionization energy can be obtained the group 18 noble gases or rare gases. The lowest first ionization energy can be group 1 elements, right? Group 1 elements. Those are the alkali metals. Okay, let's write down these things. Write down here. According to the graph, noble gas elements in group 18. Noble gas elements, according to the graph, noble gas elements in group 18. Noble gas elements in group 18. Noble gas elements means rare gas, also current. Noble gas elements in group 18 lie at the peaks, the peak points, lie at the peaks. Stop. Thus, they have the highest first ionization energy. Thus, they have the highest first ionization energy. Thus, they have the highest first ionization energy. Highest first ionization energy. Next point. The next point. This is because they have very stable. This is because they have very stable, fully filled. Very stable, fully filled. This is because they have very stable, fully filled outermost shells. Outermost shells. That's the point, okay? Outermost shells in their neutral state, otherwise we are going to tell in their ground state, their neutral state or their ground state, right? Okay. Then let's write down next point. Elements in group 1 lie at the troughs. Elements in group 1 lie at the troughs. Elements in group 1 lie at the troughs. Full stop. Thus, they have the lowest. First ionization energy. Thus, they have the lowest first ionization energy. Thus, they have the lowest first ionization energy. Okay, next point. For transition metals in the D block, for transition metals in the D block, the first ionization energy does not show the first ionization energy does not show a regular increase, across a period, regular increase across a period, comma, but a gradual increase is observed. Does not show a regular increase across a period, comma, but a gradual increase is observed. The gradual increase can be shown here. A gradual increase is observed. Okay. Now let's write down second ionization energy. Write the topic as second ionization energy. The complex things now up to now we have already done. If you can understand the first ionization energy, there are no takes under the second and third ionization energy is same as first ionization energy. Look at this. Okay, when we consider the second ionization energy, how to write the common equation for this? When you are writing the common equation for the second ionization energy, right? Look at this. What will be the previously we have written the common equation of the first ionization energy. Do you remember about that? Then how did we write that? This should be gaseous state, brown, gaseous state, ground state at after releasing loosely bonded electrons from the valence shell, it can be produced the unipositive gaseous state ion. The product of the first ionization energy equation is the reactant of the second ionization common equation. The product of the first ionization energy equation is the reactant of the second ionization energy common formula, right? What will be the reactant here? The reactant of the second ionization energy is the unipositive gaseous state ion. After releasing electrons from the unipositive gaseous state ion, it can be produced the divalent, right? Divalent or dipositive. Previously univalent or unipositive. This is the divalent or dipositive gaseous state, right? Then how to define the second ionization energy? Remember this, every time it should be released only one electron. It cannot be released 2 or 3 or electrons when the occurring of the ionization energy, right? Okay, when we consider second ionization energy, that's how to describe that. Energy to remove an electron from a unipositive cation to form a dipositive cation, right? Same as we are able to describe the third ionization energy also. Then how to describe the third ionization energy? The energy to remove an electron from the dipositive cation to form a tripositive, it means trivalent tripositive cation, right? Okay, that's how to write down this. Okay, here also there are several peak sheets. What will be the peak points here? Okay, let's draw that. When we are drawing the graph of the second ionization energy, the y-axis should be the y-axis should be IE2. X-axis shape as previous one. I have told you the shape of the first ionization energy or second ionization energy graphs are the identical, and also third ionization energy also identical. But the element that we are going to start, it's different, right? We have told it now. The elements that we are going to start, it is different. Then tell me the same shape. This shape is identical for the first ionization energy graph. This is, I am going to draw the second ionization energy graph. Okay. Then tell me which element that I am going to start this from. Previously I have started hydrogen. I have told you if it is first ionization graph, we are going to start hydrogen. If it is second ionization graph, we are going to start helium. Now we are going to start helium. Then helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, argon, potassium, calcium. Here I am not going to write this point, right? Look at this. Now, are there any 2 electrons for the hydrogen? No, only 1 electrons is included first energy level in the hydrogen atom. Due to that reason, it cannot be released 2 electrons. That's the main reason for it cannot be obtained the value for the second ionization energy of the hydrogen. That's the main reason for starting from the helium here, right? Okay, when we consider the peak points of the second ionization energy graph, what are the elements that can be obtained the peak points? These are the first group elements, no? Lithium, sodium, potassium. Look at this. Lithium, sodium, potassium are the peak points elements in the second ionization energy graph, right? Look at these. Group 1 elements now sit at the highest peaks because they have achieved a stable noble gas configuration after losing one electron, right? That's the main reason. What will be the trough points? What are the elements in the trough points in the second ionization energy graph? Tell me. Second group elements. Then second group elements can be obtained the lowest second ionization energy values. Previously, do you remember which group elements can be obtained the highest and lowest first ionization energy? Tell me. The trough point can be obtained the first group elements. The peak points can be obtained the group 18 elements. Then here also the trough point can be obtained the second group elements. The peak points can be obtained the first group elements. Likewise, there is a pattern. Right? Okay, let's write down these things. Write down here. Write the topic as second ionization energy. Then after that, let's write down not the energy required to remove 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 an electron from a gaseous unipositive cation. A gaseous unipositive cation. The energy required to remove an electron from a gaseous unipositive cation. Underground state conditions. Underground state conditions. To form gaseous dipositive cation. It means gaseous divalent cation, right? Gaseous dipositive cation. Gaseous dipositive cation is the second ionization energy. Is the second ionization energy. That's how to define the second ionization energy. Right? Previously, I have mentioned about this. Okay. Then write the common formula for this. Write the common formula. The common formula should be like this. Write down this equation. And also substitute values for this. Substitute sum of elements. Now let's substitute sum of elements for this common formula. When we are writing the second ionization energy of the magnesium. How to write the second ionization energy of magnesium? Tell me. Magnesium should be in the gaseous state and it should be unipositive. After releasing electron, then it can be produced the another positive ion. After adding another positive ion to this unipositive ion, it can be converted to the dipositive ion, but it should be in the gaseous system. Right? That's how to write the every time. If it may be first ionization energy or second ionization energy or third ionization energy, every time it should be released only one electron. We are not going to release 2 or 3 electrons immediately, right? One by one, we are going to release one by one electrons corresponding to the first and second and third ionization energies, right? Okay. Now, let's draw this graph. Before that, write down here. Right down here. The second ionization energy graph for 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 elements with atomic numbers elements with atomic numbers elements with atomic numbers elements with atomic numbers 1 to 20 is shown below. 1 to 20 is shown below. 1 to 20 is shown below. Okay, draw this. Draw this graph. Right. Right. Highlight the peak elements of the second ionization graph and the trough elements of the second ionization energy graph. As you can see, the peak elements can be obtained the first group elements and also trough elements can be obtained the in the second ionization energy graph from the second group elements. Okay, let's write down these things according to this graph. Write down here according to the graph. According to the graph. According to the graph. According to the graph. Group 1 elements are at the peaks. Group 1 elements are at the peak. Right? Group 1 elements are at the peak. Group 1 elements are at the peaks. Thus, group 1 elements are at the peaks. Thus, the highest second ionization energy. Thus, the highest second ionization energy belongs to the highest second ionization energy belongs to the highest second ionization energy belongs to group 1 elements group 1 elements group 1 elements the highest second ionization energy belongs to group 1 elements. Okay, the next point, write down next point. Group 2 elements are group 2 elements are group 2 elements are at the troughs group 2 elements are at the troughs full stop. Thus the lowest second ionization energy thus the lowest second ionization energy the lowest second ionization energy belongs to the lowest second ionization energy belongs to group 2 elements. The lowest second ionization energy belongs to group 2 elements. Okay. As you can see, when the electrons are released from the ground state atoms, they can be moved from first ionization energy to second ionization energy to third ionization energy. After releasing electrons one by one, when we consider the gaseous atom in the ground state, after releasing loosely bonded electrons from the valence shell, it can be produced the gas state monovalent cation. The common formula known as the first ionization energy, right? Then when we consider the second ionization energy, that's how to write the second ionization energy form. When we consider third ionization energy, that's how to write the third ionization energy formula, common form, one reaction, right? It means for any given element, right? When we consider for any given element, then tell me the second ionization energy of that element is greater or lower than the previously first ionization energy. The second ionization energy should be greater than the previously first ionization energy. The reason is when the electrons are releasing from the valence shell, the valence shell is gradually near to the nucleus of that element. It means distance between nucleus and the valence shell decreases. If the distance between nucleus and the valence shell decreases, then is it easy to remove the electrons from the valence shell? No, difficult to release the electrons from the valence shell. It's difficult. The reason is attraction forces are highly bonded, high, right? In that situation, it has the high attraction forces between nucleus and the valence shell electrons. That's the main reason. Then when we consider for any given element, the second ionization energy is greater than the first ionization energy, and also third ionization energy is greater than the first and second ionization energy. Right? Remember about that point. That's very important. Okay, let's write down this also. Write down here. Sorry, important point. Write down here. For any element, the first ionization energy is less than. For any element, the first ionization energy is less than. The first ionization energy is less than the second, which is less than the third, which is less than the third, Okay. Now we are in the second ionization energy, right? Now we are going to move another ionization energy. It is known as the third ionization energy, right? Okay. Try to write down this first of all. That is the point I have already mentioned here. Write down this point. Now you need to write down fundamental law. Write down for any given element, the second ionization energy is greater than the first ionization energy, and also third ionization energy is greater than the first and second ionization energy. After that, write down the topic as third ionization energy. Third ionization energy. Right? These are very simple. Today I am going to complete this lesson. Right? This is an important lesson. In your A-level exam, they have given the several questions under this topic. Right? The unit 1. This is very important topic among the topics of the group 1. So, unit 1. Right? Okay. Let's write down. Tell me how to define the third ionization energy. It is the same as first and second ionization energy. Right? Then tell me how to define them. Then what will be the reactant of the third ionization energy in the common formula? The reactant should be product of the second ionization. It means it should be in the ground gaseous state, dipositive ion. After releasing loosely bonded electrons from the valence shell, it can be produced the tripositive or trivalent gaseous state ion. Then how to tell that? Energy to remove an electron from a dipositive cation to form a tripositive cation. Right? Okay, let's write down that. Write down. The energy required to remove an electron. The energy required to remove an electron the energy required to remove an electron, the energy required to remove an electron from a gaseous dipositive ion, from a gaseous dipositive ion, from a gaseous dipositive ion. Underground state conditions, underground state conditions, underground state conditions, underground state conditions to form a gaseous tripositive cation, gaseous tripositive cation, gaseous tripositive cation, gaseous tripositive cation is the third ionization energy, is the third ionization energy, is the third ionization energy, is the third ionization energy. In the brackets, write down IE3, IE3. Okay, write the common formula. Write down the common formula for the third ionization energy. Right? The reactant should be gaseous state dipositive ion. The product should be gaseous state tripositive or trivalent cation after releasing electron. Now you are able to see there is a pattern here. When we consider the third ionization energy graph, right? Now, which type of element that I am going to start this graph? Which element? The first ionization energy we have started hydrogen. If it is second ionization energy, we have started second element, helium. If it is third ionization energy, we are going to start from the lithium. The reason is, when we consider the ground state helium atom, it cannot be contain 3 electrons. No? The atomic number of helium is 2, then it cannot be contain 3 electrons. At least 3 electrons are contained lithium. Due to that reason, we are going to start from the lithium here. Then lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, argon, potassium, calcium, like this. Now I am going to erase this part, right? This is how to draw the third ionization energy graph. What's the reason to erase this point? There are no elements here, no? Right? After the calcium, are there any elements here? No, cannot be included, right? Okay. Then tell me which group elements are in the trough points and the peak points. Peak points, group 2 elements, right? The highest third ionization energy values can be obtained group 2 elements. The lowest third ionization energy values can be obtained group 13 elements. Group 13 elements. Then, as you can see, there is a order here. That's order. What will be the order? Then remember again, which group has the highest first ionization energy? Group 18 elements. There's another name for the group 18. Zero. Noble gas 0 group means it also the group 18 group. Okay. Then, which group has the highest second ionization energy values? Group 1 elements. Group 1 elements. Right? Group 1 elements. Like this. Then, which group has the highest third ionization energy values? Group 2 elements. Right? Then tell me, which group has the highest N ionization energy values? Then it should be N-1 group. N-1 group elements. Highest first ionization energy can be obtained 1. If it is first ionization energy, 1 minus 1, it's equal 0. Then 0 group means group 80. Highest second ionization energy values means second ionization energy means we are going to substitute the value for the end second. Then 2 minus 1, 1. Then which group has the highest second ionization energy value? First group value. Then highest third ionization energy values 3 minus 1. Second group elements likewise. That's order. Right? Now you are able to identify which group has the highest first and second and third ionization. Right? Okay, let's write down these things. Under the third ionization energy, now we are going to draw the graphing. Okay, first of all, write down here the third ionization energy graph. 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 The third ionization energy graph for elements with atomic numbers for elements with atomic numbers 1 to 20 is shown below. 1 to 20 is shown below. Okay. Then same as previous one. Now let's draw the third ionization energy graph. Okay. No need to draw this. We have already drawn previously also. Try to draw this. Right. Same as previous one. The shape is identical. The shape of the third ionization energy graph is identical first and second ionization energy graphs. Right. The starting initial element can be changed. It can be changed. Right. Okay. Let's write down. Then write down here. According to the graph, group 2 elements, according to the graph, group 2 elements are at the peaks. According to the graph, group 2 elements are at the peaks. Group 2 elements are at the peaks, comma. So, full stop. Thus, the highest third ionization energy belongs to group 2 elements. 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 Next point. Group 13 elements. Group 13 elements are at the troughs. At the troughs. Group 13 elements are at the troughs. Group 13 elements are at the troughs. So stop. Thus the lowest third ionization energy belongs to group 13 elements. Group 13 elements. Group 13 elements. Group 13 elements. Next point. Okay, now let's write down Now we are going to consider next of the successive ionization energy graphs. Before that, we have to do past paper questions under the ascending or descending order of the ionization energy, or the successive ionization energy part, right? These are questions that they have given to prepare the ascending or descending order of the ionization energy, right? We will write several questions and let's consider how to solve the question. Okay, look at this. The question mark. What is the correct order of increasing first ionization energy for sodium, magnesium, potassium, nitrogen, phosphorus, and fluorine? Right? Okay, let's write down this question. First of all, this question is included in your tute also. Yes. This is the past paper question. The 2013 A level, the increasing order of first ionization energy of atoms. No, it is not this question. No, but we are going to write down this question also. 9 question, mark the question number 9. Question number 9, mark these questions. And also another question is, they have given the questions to prepare the ascending or descending order. Next one, 2021, we have given the question, the decreasing order of first ionization energy of hydrogen, helium, lithium, beryllium, boron, and sodium. Right? Okay. Question number 31. The next question is, okay, these are the main questions, but these are the past paper questions below 2010. Right? From 2012 to 2025, questions are included in this tute, right? But now I am going to give you the question below 2010. Those questions we are going to write in the tute, right? Question. What is the correct order of increase in first ionization energy? This is the question. What is the correct order of increase in first ionization energy? First ionization energy for sodium, magnesium, potassium, nitrogen, phosphorus, fluorine. For sodium, magnesium, potassium, nitrogen, phosphorus, fluorine. Right? Okay, no need to give the answers. I am not going to give you the answers. Now I am going to tell you how to solve these questions, these type of questions. When they have given the questions like this to prepare the ascending or descending order, what we are going to do? What we are going to do here? If they have given the question ascending or descending order, we are going to check whether it is first ionization or second ionization energy or third ionization. If it is first ionization no, second ionization no, third ionization energy, it's not a problem. Same graph, the shape of the graph is identical. But the element that we are going to start this, label this graph, if it is first ionization energy, we are going to start from the hydrogen. If it is second ionization energy, we are going to start from the helium. If it is third ionization energy, we are going to start from the lithium. I have already told these things, but every time, right, they have given the first ionization energy. Now, at the beginning, I am going to draw it. Right? I will draw at the beginning. Look at this. Look at the pattern. That's how to draw. Okay. This is the pattern, zigzag pattern. I have told you there is a line here. There is an element below this line, and also there is another line here. There is an element above this line. Repeat this part, zigzag part from here, and end of the zigzag part should be end of the line. Then complete that final part and also attach these points and also Attach this one. Now it's already complete. You should have the ability to draw this graph immediately, right? Okay, now if this is first ionization energy, you are going to start from the hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. Otherwise, there's another method. The elements that they have given for us, you are able to write down here. No need to write down all of the elements, right? Fluorine, neon, sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, argon, potassium, calcium. Right? Okay. Now, the elements that they have given for us, sodium. Now, I am going to highlight these sodium. The next one, magnesium. Then potassium is the point. Potassium. Then nitrogen. Here is the location of nitrogen. Phosphorus. This is the location of phosphorus. Next one, fluorine. Then tell me ascending order of this element. How can we increase these elements, ionization energy of this element? The lowest ionization, first ionization energy can be obtained first group elements, right? Then potassium, and next one should be Kelvin. Sodium. The first ionization energy of the magnesium is greater than the first ionization energy of sodium. Potassium, sodium, magnesium, the next one phosphorus, the next one nitrogen and fluorine. Nitrogen and fluorine. It's very simple. That's how to write the, that's how to prepare the ascending order or descending order. Right? These are the past paper questions. Okay, let's write down. Clear the question. Answer it. First of all, draw this. After drawing this, write the answer. Hurry. Write the methods how to obtain the answer. Okay, let's go to the another question also. This is also the past paper questions. Write down. Question 2. What is the correct order of increasing? What is the correct order of increasing? What is the correct order of increasing? First ionization energy for elements. First ionization energy for elements from lithium to fluorine. First ionization energy for elements from lithium to fluorine. Right? Using this graph, you are able to obtain the answer. It's easy. From lithium to fluorine, these are the elements. Then tell me how to deviate this element. Which element has the lowest value? You know, lithium. Lithium has the lowest value. Then lithium, the next one should be boron. The next one shouldn't be the beryllium, it should be the boron. The next one, beryllium. Another one, carbon, oxygen, nitrogen, and fluorine. Lithium, boron, beryllium, carbon, oxygen, nitrogen, fluorine. That's how to obtain the answer. Right? We are unable to obtain the answer without this graph. Okay. First of all, if they have given like this question for you, try to prepare the ascending or descending order of our first ionization energy or second or third ionization energy. First of all, you have to draw the graph of the 20 elements. The shape of the first or second or third ionization energy are identical, but the element that we are going to start is different first and second and third. If it is first ionization energy, we are going to start from the hydrogen. If it is second ionization energy, we are going to start from the helium. If it is third ionization energy, we are going to start from the lithium. It's very simple. This is the first, this is the one of the method that they have given the questions for the your A-level Excel. Right? Okay. Do you remember? Can you understand those things? Okay. How to get the answer? There is another method. There is another method, another question method that they have given for us, right? Today, up to now, I'm not going to discuss so far. So far, we have discussed we have already covered ionization energy, but there is a remaining things that we have to do. Those are there are several methods. We have already done one method. This is the one method to give the questions from the ionization energy, and also this is the method that we are going to apply the theories we have already learned. Theories, not only learn theories. That's not enough for the A-level exam. You have to apply these theories for the questions. These are the past paper questions. And also there are several past paper questions inside this tube, right? You have to do, you are able to do these things. And also there are exam target questions also inside this tube, right? MCQ questions and structured essay questions. Try to do those things. At the end of the lesson, I am going to complete this tube. And also we have already discussed several questions inside this tube, right? Okay, there's another method. I'll discuss that method after discussing successive ionization graph. There is only one remaining thing that we have to discuss under the ionization energy. This point, I will discuss this point next day when we are beginning at the beginning of the class, right? Okay, that's enough today. Are there any questions under these points that we have already discussed so far? No? If you have questions, then okay, right. Hari ටික මොනාරි ප්‍රශ්නයක් තිබ්බොත් කියන්න. හරි. right අපි මේ ටික